All right, so number one tells us that we need to find the average speed of a car that's traveling 135 miles in 2 hours. Well, super simple problem. You just need to remember what is your formula. And your formula for finding speed is speed, or S, equals distance, or D, divided by time, or T. It's not being lazy. And that's your formula. So you have both the distance, 135 miles, and the time given to you. So all you need to do is do a simple substitution problem. So S is, in this case, the distance was 135 miles. And time is 2 hours. I forgot to put the units for distance. It's miles. Units are important. And now you simply crunch out your math and you get some kind of an answer. And the answer in this case, unless my math is wrong, is 67.5 miles, or MI, per hour, or just H. So breaking the speed limit a little bit here in the state of California, but not by much. Any questions? So number 2 says, if you run an average of 6 meters a second, how long will it take for you to run a track that is 400 meters long? Good question, and a similar question to number 1. We're going to use the same exact formula to find the answer to this problem. So the formula was S equals to D. So speed is D, distance, over time. 400-meter track, that's a pretty standard track. Most high schools have that kind of a track, so here I have an awful representation of that. Yay. Now you're given the speed and the distance, but you're asked to find the time. So when you do your substitution, you're substituting in different spots, and instead of finding speed, you're actually trying to find time. So let's go ahead and do that. Let's substitute speed, which is 6 meters a second, or 6 ms. And distance in this case was 400 meters, or 400 m. And time is still an unknown, so we're going to leave it as t. You could use anything else, but why change a letter when it's already there? Now, you're doing a simple pre-algebra level single variable equation that you're going to be solving here. You're solving for t. You're going to isolate t. And the easiest way to do that is by cross multiplication. The 6 meters per second, you can think of it as being divided over 1, so there's a 1 there. So it's going to be 400 times 1, or 400 meters, wrong color. Time is 1, or just 1 for that 1. You don't even have to write it. Equals to 6 meters per second times the t that we're also desperately trying to find. Next step, isolate t by dividing both sides by 6 meters per second. It's pretty easy, pretty standard, again, pre-algebra level problem here. On the right side, this simplifies down to 1, or it's gone. On the left side, the meters cross out or simplify out, and then you're left with 400, well, this one is also gone, so 400 divided by 6, which is 66.7 if you round up to the 10th place. I'm going to do that. So T equals to 66.7, and the only unit that's left is seconds. So that is your answer. That would be the time it would take you to run a 400-meter track. That's a pretty, well, it's an average time. Not a great time, but I guess this person is not an athlete. Questions? Number 3, I'm not going to have a problem there because it requires no calculations. It says a car speedometer reads 60 kilometers an hour. So pretend you're not in the United States. Everywhere else it's kilometers an hour. Can you say for certain that a car's velocity is constant? Explain. Well, no, because velocity is a vector, and vectors require direction. So velocity is speed in a particular direction. So we have the speed, 60 kilometers an hour, but since I have no idea what direction that particular vehicle is going, I can't say that the velocity is constant, because if that car is taking a turn, the velocity will be changing. Actually, it will be changing constantly as the turn goes on. The car will not be going in one direction. So if that car is going in a straight line, then yes. But if that car is taking any kind of a turn, even if it's a very small turn that you can't even feel, the velocity will be changing because the direction will be changing. Questions? All right, number 4, you're given this particular graph and you're asked to essentially interpret this graph or describe it. So you should have one in your worksheet very similar to this. It's a distance versus a time graph. And can someone tell me, what does distance versus time measure in a graph? Speed. We measure speed in a distance versus a time graph. So how much distance are you covering at a certain amount of time? If you divide distance by time, you get speed. So in this graph, 3 things are happening. You have this section here, you have that section there, and then you have this curvy section all the way at the end. So they don't tell us exactly what's going on. So the best explanation that I can come up with is this is a person who was walking, and this first bit here, it's a straight line without any curves. So the slope, if you were to measure it out, would be constant. So if the slope is constant, the speed is constant. So for a distance of whatever it was, 8 meters, 9, 10 meters in your worksheet, this person is going at a constant speed, not changing. And then once he reaches that point, nothing happens. Time is going, but there is no distance being covered. So if you were to do that math, you would get the speed is 0 because time is changing, but since distance is 0, 0 divided by whatever the time is, that's 0. So the speed here is 0. That person stopped. I don't know what he was doing, but he stopped. My guess is he forgot something. He's rummaging through his pockets to see if he has it. And then he goes, darn, I forgot something at home. So now I have to go back home. The last bit, he is now covering the distance backwards, and it's a curvy line. So what's happening here? Why is it curvy? Well, I think here he was relaxed. He was going at a constant speed. He's a little frustrated. So as he's walking, he may be changing his speed, going a little bit quicker, a little bit slower. So here the speed is variable. The speed will change. The speed is changing. It's not constant. The slope is not constant throughout. So constant speed, 0 speed, variable speed on the way back. Questions? All right, so for number 5, you're asked to think of a trip that you just took and approximate the total distance and the total time it took, then calculate the average speed And lastly, explain how instantaneous speed varies over the course of the trip. Sure, not a problem. So since I lack imagination, I took the most recent trip that I took, and that was from work to home. Work here at GHS, home where home is. And the approximate mileage that I travel is about 15 miles. I have a fairly short commute, and it takes me about 18 minutes. This will obviously vary from day to day, but on average takes me about 18 minutes to get here. Again, a pretty short commute. Now, I can easily calculate that out by dividing distance over time to get my speed. Apologies. And this would be my average speed. So I take the distance, 15 miles, divided by the time it takes me, 18 minutes, and I get 0.833 miles a minute, which is a weird measurement. If I were to multiply that by 60, I would get 50 miles an hour, 60 minutes in an hour. So my average speed is 50 miles an hour. That's actually not bad at all. I spend most of my time, going fairly quickly. So that is my average speed. Your average speed would vary depending on your trip, where you were going, the medium of your trip. Were you in a car, a plane, a boat? Were you going by foot or bicycle? So obviously yours and mine would be different. The last part is explain how instantaneous speed varied over the course of the trip. Now, unfortunately, it's not a direct route with no stop signs between work and home. So I encounter several stop signs and, depending on how lucky I am, several green or red lights between my house and my work. So every time that happens, I accelerate from a stopping point or from the parking lot, and then I have to stop at a stop sign or a red light. Then I accelerate again, I stop somewhere at a stop sign or a red light, and this keeps going until I get home and I stop finally. So my instantaneous speed will be varying. I will be accelerating, deaccelerating, accelerating, deaccelerating, accelerating, deaccelerating. So I'm not going 50 miles an hour the entire time. At times I'm doing 0 miles an hour when I'm waiting in traffic. At times I could be doing upwards to 60 miles an hour, which I'm pretty sure I'm breaking a speed limit in a few places if I'm doing that. But hey, any questions? All right, number 6 says an ice skater glides around the rink at a constant speed of 2 meters a second. Is a skater accelerating? Explain. Again, I'm not going to have a problem in front of us because it's not going to require any calculations. Now, if you recall from our lesson, you will know that acceleration is a change in time for a velocity over a course of time. So it's velocity over time. How much time changes for a certain velocity. So velocity being a vector, you have to be going in a straight line for your velocity not to change. And if you've never been to an ice skating ring, it's pretty similar to a track. Well, it's oval shaped. And if you're going around it, you are going to be changing directions quite rapidly, actually, at some points. So your direction will be changing. So even though you're going 2 meters a second, your direction, you're going to be facing north, south, east, west, all over as you are going around that rink. So yes, you are going to be accelerating. Every time you change direction, you will accelerate. And that's that. Questions? All right, number 7, we have another graph, and we're asked to interpret or describe this graph as well, or what's happening here. Well, the first thing you want to notice is this is a velocity versus a time graph. And in velocity over time, what are we measuring? We're measuring acceleration. So this graph will show us if there is acceleration, deceleration, or no acceleration, depending on the slope. A positive slope gives us acceleration, a negative slope gives us deceleration, or slowing down, and no slope gives us no acceleration at all. So let's look at the graph. Going from A, which I forgot to mark, to B, you have positive slope. If you were to calculate the rise over run here, it would be some kind of a positive number. So from A to B, you are accelerating. And again, you can easily do the math. I did not put the units on my graph. You have units on there, and you could easily calculate out the slope. But the point being, you would get a positive slope. You would get some kind of a acceleration. B to C, there is no slope. That means there is no acceleration. There is still velocity. This car or person or whatever we're tracking here did not come to a stop, because whatever velocity was here on your graph, that's about 20 meters per second, that object is still going at that velocity, so it did not stop, but it stopped accelerating. So you could say that, let's say if this is a car, from a stop sign to a certain cruising speed. Then from C to D, the car floors it again, accelerates to an even faster speed, about 40 meters per second. And then once it reaches D, it's cruising again. There is no slope from D to E. Again, the car is moving, so there is still a certain velocity as time goes on, but there is no change in velocity, which means there is no acceleration. Then from E to F, we have a negative slope. If you were to calculate the slope of this, you would get some kind of a negative number, which means that we have the acceleration slowing down. From E to F, the brakes are being applied and the car is slowing down to about 20 meters a second. From F to G, again, the car is moving slower, but it's moving at a constant velocity with no acceleration. And from G to H, the car accelerates again, getting up to 30 meters per second. So here you have positive slope, you have acceleration. Acceleration, positive slope, no acceleration. Acceleration again, positive slope, no acceleration, no slope. Negative slope, deceleration. Zero slope, no acceleration. Positive slope, acceleration. Questions? All right. So number 8 says a downhill skier reaches the steepest part of a trail. So that's my infographic that will resemble whatever they just said. Don't make fun of my graphics. Her velocity, probably should have added some hair there, increases from 9 meters per second to 18 meters per second in 3 seconds. What is her acceleration? Well, there's a formula for that. Can someone tell me what is the formula to solve that particular problem? Well, if you were thinking of that, congratulations. If not, you need to do some more studying. Acceleration can be measured by coming up with the final velocity, or VF. Subtract from that your initial velocity, or VI, and divide that result by, or the difference, by the time it took in that particular interval. Luckily for us, they gave us all that information. They told us what the final velocity would be once she reaches her top speed. We assume, we don't know, but given what we're given, is 18 meters a second. We also know the initial velocity, again, not from a stop, but the initial velocity before she began accelerating quickly was 9 meters a second. And all of this happened in 3 seconds. That was the interval. So if you plug everything in, so now I have everything plugged in. Our final velocity, or VF, minus our initial velocity, or VI, and divided by 3 seconds, which is our time. Well, now it's just simple mathematics. It's not even algebra. Calculations. 18 minus 9, that's 9 meters per second. No. The time did not change, obviously. It's still 3 seconds. And what is 9 divided by 3? 3, of course. You will see that you will have meters per second divided by second. So this is going to be your acceleration, meters per second squared. So meters per second squared. And that's it. That is the answer to the problem. The acceleration she experienced from the top of the hill to the bottom of the hill, or whatever she was doing, the steepest part of the hill, was 3 meters per second squared in that segment of time. Questions? All right, let's take a look at number 9. Another cyclist problem. Here they say a cyclist comes to a sudden stop going from 16 meters a second to 0 meters a second in 4 seconds. What is their acceleration? So here you have a cyclist. I'm not sure about the gender, male or female, doesn't really matter. And they're, bicycling along just fine. Then they have to stop because there is a very cute kitty up, right in front of them, and they don't want to run over that cute little kitty. And if you've ever come to a sudden stop in a bike, there's a chance you are flying face first, but those are personal experiences. Who knows? This could be a more experienced cycler, but that's what my infographic shows. At any rate, they are asking for acceleration. This is identical to the problem before, exactly the same problem. So we're going to use the exact same formula. So this is the exact same formula. Acceleration is your final velocity. You subtract from them your initial velocity, so the difference between final and initial. And you divide all that by the time segment that this all took place in. Well, we know both. We know that the final velocity was when the bicycler came to a stop, bicycle as well, was 0 miles a second, or meters a second. Ooh, that would be really quick. So once again, do your simple calculation. What's 0 minus 16 meters a second? Well, it's a negative 16 meters a second. And hopefully negative numbers are not an issue for any of you. If they are, I'm truly sorry. Go back to math. You're dividing a negative number by a positive number. Rules of pre-algebra state that your outcome will be negative. And 16 divided by 4, we're not going to go into detail here. It's 4 meters per second squared again. It's a negative number, which tells us what? For acceleration, it's a negative acceleration or a deacceleration. So this person accelerated in a negative direction because they were stopping, and this is how quickly they deaccelerated, 4 meters a second squared. If you compare that to our last problem, this was a pretty sudden stop. So again, why I think this person is flying off their bike, but who knows. Questions? Last problem, number 10. We have a 1,500 kilogram car, yay car. It's moving at 12 meters a second. What is its kinetic energy? Well, there is a formula for that. What is it? There it is. See how smart you are? So the kinetic energy can be calculated by using this formula, 1/2 times mass times speed squared. Now, fortunately, we're given everything that we need here. We're given the mass, which is 1,500 kilograms. We're given the speed, that's 12 meters a second. So if you substitute everything in this formula, you should find kinetic energy. So let's do that. So kinetic energy is going to be still 1/2. Let me do the substitution. Terrific, terrific. So now we're ready to do our final number crunching. And if you remember your order of operations, exponents trump everything else. So 12 times 12, that's 144 Here you have still your 1500 kilograms, and and I'm going to go ahead and do that calculation here. Half times 1500, that is, or 1500 over 2, that's 750 to save us a step. Again, 750 because 1/2 times 1500. Oops. And now you do some more number crunching by multiplying 750 by 144. Oops, I forgot to put the powers of 2 here because our units also got exponentially multiplied. Meters times meters, meters squared. Second times second is second squared. So let me put them back here. And that is your answer. 10,800 kilograms times meter squared all over second squared. And if you left it like that, perfect. And if you knew that this is actually a joule, capital J, you can write that in, but this is perfectly valid. Joule is just a shorthand for writing that monstrosity. Questions? Thank you.